Now, here's another consideration for a pumped system. The use of a motor. Here I've got a pumped system. Now, I know you haven't used valves yet. You haven't done valve control yet, or valve theory. But vaguely speaking, for efficient use, if I was sizing a valve so that it would be a good control over the whole range, what would the valve position be at nominal flow? Now, nominal flow means the flow at which it's normally running. So normal running conditions, what sort of position would you expect the valve to be in? Yeah, you'd expect it to be running about 50%-ish, yeah? So that it's able to control up and it's able to control down. In reality, we probably would be running it more open. When we talk about valves, we'll go into the details of that. So if your valve is normally run at 50% open, let's say, for the sake of argument, that I put a VSD on the pump. I'll put a VSD on the pump and I'll open the valve to 100%. So, what do you reckon? I'll run the pump at 50% speed? Does that seem fair? Okay, so I'll run that at 50%, which will be 25 Hertz. How much energy saving, or how much energy do you think the motor will use compared to normal running? In actual fact, a funny thing happens. The energy saving for a centrifugal pump or a fan is proportional to the cube of the speed. What that means is if I reduce the speed to 50%, it uses only 12.5% of the power. So, for that reason, VSDs, we always say that a VSD pays for itself in 18 months. A VSD will pay for itself in 18 months in energy use alone. So, because the energy saving is so huge, a VSD always pays for itself. In actual fact, it's better than that. Going back to this drawing, if I was to, grab a pen here, if I was to get rid of the valve altogether and simply pipe that across, what happens is my system resistance is now reduced by half. So I don't need to run the VSD at 50%. I actually only need to run the VSD at 30%. And if I run the VSD at 30%, my energy use drops even more. It drops to something like 8%. So when it comes to valves and this type of pump system, the first question you have to ask yourself is, do I need a valve? Because if I can get rid of the valve and VSD control the motor, I will save massive amounts of energy. Yes, there are problems with running things slowly, of course. But then, because you know you're going to be doing it, you size everything appropriately. Now, another consideration, and this is getting back to John's issue at the beginning, another consideration about VSDs. Let's do a comparison of a VSD versus star delta starter. For a VSD, I've got three-phase in, through my VSD, to a motor. That's all I've got. star delta, 3-phase in, my first contactor. I'm worried about phase, so I'm going to put a phase checker there. I want to measure the current, so I'm going to put a CT there. Then I've got my star contactor over here, and I've got an overload on that. I've got a timer, which is going to bring in my delta. I've got my delta contactor here, and I've got an overload on that. I've got 2 sets of wires going to the motor. What I haven't drawn in is over here, I've got power factor correction. I don't need that for the VSD. So I've also got power factor correction over here. Now, putting on my shift electrician's hat for the moment, I see this side of things as a whole bunch of call-outs. The VSD does go wrong. The VSDs go wrong. They do funny things. They go wrong. You walk up to it, you press the reset button, and it starts back up. If it does anything silly, anything even sillier than that, if it starts behaving really, really silly, then I call in the specialist. I call the manufacturer, and I get him to come out and look at it. So this, over this side, the star delta starter, this is just call-outs for me. This is changing contactors, overloads tripping, timer relays breaking, CTs crapping out. I've got all the power factor corrector rubbish. I've got 2 load of wires to run to my motors. Over here, I've got 1 wire to run to my motors, an easy install. And if the silly thing does go wrong, then it's SEP. Somebody else's problem. That's why I like VSDs. Because, well, I'm lazy. Anybody got anything to say about this? Okay, moving on then. This is how a VSD works. Yeah. Somebody else's problem doesn't work when you're in the middle of nowhere, I'll give you that. But then nobody can blame you that much either. You know, you can throw your hands up and say, well, it's not my fault. Now, this is how a VSD works. What it does is, it takes whatever AC is available, and it turns it into DC. So here, it's DC. At this point here, it's turned it into DC. And then, it turns it back into AC. What this means is that it doesn't matter what's happening to the AC on the line. If the AC on the line loses a phase, it doesn't matter. In fact, you can run a 3-phase motor off of a GPO. You can put single phase into a VSD and get 3-phase out. All it wants is enough power to generate its DC voltage. Providing it's got the power to generate its DC voltage, it doesn't care. Now this is beautiful, because if the power generator decides to mess us about by dropping one of the phases or browning out a phase, normally your motor would single phase itself to death within a few minutes. But not if you've got a VSD, because a VSD just takes whatever's on the line and turns it into DC. It doesn't care. You can feed it with anything. You can feed it with the power coming off of a wind generator, which is constantly changing. It doesn't care as long as it can pull the power off, because all it's going to do is turn it into DC anyway. So the VSD-driven motors are completely immune to whatever the people decide to send us. And as they privatize the electricity companies, they will become less and less careful with what they send us. So VSD motors can survive nasties on the AC line. Now what we do is we turn it into DC, and then we turn it back into AC. But AC at a frequency of our choosing, because of course the frequency dictates the speed at which the magnetic field rotates. And the magnetic field, so here's a magnetic field, as the magnetic field rotates, then the rotor in the middle, which is to all intents and purposes a magnet, rotates to try and chase the magnetic field. So if we can change the frequency, we change the speed at which the magnetic field rotates. If we change the speed at which the magnetic field rotates, we change the speed of the motor. So we take DC, AC, turn it into DC, and then turn it back into AC, but at a frequency of our choosing. That way we can change the speed of the motor. The way we create the voltage is by using pulse width modulation. Pulse width modulation. Now this is pulse width modulation of a PLC. It's saying a duty cycle of 1/10. Pulse width modulation at around about 100 kilohertz. So we're going to pulse width modulate somewhere between 10 and 100 kilohertz duty cycle. And we're going to pulse width modulate between 0 volts and our maximum voltage is around about 600 volts. When we want to get a quarter of the voltage, say 150 volts, what we do is we turn it on for a quarter of the duty cycle. I'm going to get to talk in a minute. And we turn it off for 3/4 of the duty cycle. So that gives us the, about, on average, that gives us 150 volts average. If we turn it on for 50% of the duty cycle and off for 50% of the duty cycle, that gives us an average of 300 volts. And if we turn it on for 3/4 of the duty cycle and off for 1/4, that gives us an average of 450 volts. So we can turn the by doing pulse width modulation, we can create different voltages. So by creating different voltages in a pattern, we can create a sine wave. That's how we create the frequency of our choosing. You see, it's very easy to turn things on and off very quickly. We've got silicon control rectifiers which we can turn on and off very, very quickly. We can do this in 3 phases to get 3 phases of any frequency that we choose. So, this is what a VSD feeds. It feeds voltage out, which looks like this, and it averages out to look like a sine wave, and that voltage pushes out current, which is pretty sinusoidal. That's how it works. Okay, so that's how we use a VSD to create whatever frequency we want. We actually output, not in the frequency we want, we actually output little chunks at 10 kilohertz or 100 kilohertz. And these little radio frequency chunks go out and average out to a sine wave. And that average sine wave voltage creates a nice sine wave current. And of course it's the sine wave current which pushes the motor.